Okay, thank you all for joining this session, which is an introduction to Analysis of Variance, or ANOVA, which will be illustrated with XLSTAT. My name is Jean-Paul Maalouf. I am a statistics consultant at XLSTAT. I'm very happy to talk to you today in this last webinar of the autumn webinar season of XLSTAT. So we've already seen 4 webinars before, and this is the last one of the season. And I'll try as much as possible to use intuitive language and avoid reference to complex mathematical formula. So let's start. Here's a plan first. I start by saying, as usual, who we are, what is XLSTAT. Then I'll talk about different statistics categories, so statistical tools categories. And before switching to ANOVA, I'll do a small reminder on statistical testing. So we had one whole webinar on statistical testing. Then I'll start talking about ANOVA, and I'll start talking about it as a modeling method, so as we've seen in the previous webinar. Then I'll mention the statistical test that is involved in the ANOVA problems, before talking about conditions of validity and multiple pairwise comparisons. Then I will tell you about the Kruskal-Wallis test, which is a non-parametric equivalent for the one-way ANOVA. And at the end, I will conclude with the two-way ANOVA. So I will add another explanatory variable, and I'll talk about the two-way ANOVA and the interaction effect. So you have also appendices on the Welsh statistic and mixed models. You can check them out in the handouts. Who are we? XLSTAT is a user-friendly statistical add-on for Microsoft Excel. Many of you have already used it, but for those of you who haven't seen it yet, this is a good opportunity to check it out. I will illustrate everything with the software. Here's a small historical overview. The development started in 1993. The first sale occurred in 1996. In 2000, the Addinsoft company was created. It's the current company that develops the software. In 2006, we have a new version with 2 complementary coding languages, which are the VBA for the interface and C++ for computations. In 2009, we had new offers, which were redistributed in the form of different solutions, which are field-oriented or general solutions. In 2016, we released 2 major products, the cloud version of XLSTAT, which is XLSTAT 365, as well as the XLSTAT free edition, which is a limited edition in terms of number of features. So you can use the XLSTAT free edition without any valid license key. Without necessarily having any valid license key. In 2017, we had one major upgrade, which is the R integration. So today, we are able to interface XLSTAT with the open source statistical language R. So you can call R procedures from XLSTAT dialog boxes today, and you can configure those dialog boxes yourself. XLSTAT in a few numbers. XLSTAT has more than 200 statistical features stored in general or field-oriented solutions. We are more than 22 employees. The software is available in 7 languages. We have more than 100,000 users across the world, and more than 220,000 visits per month on the website, as well as 10,000 downloads a month. So now let me tell you about my way of storing statistical methods into 4 big families of methods. So we first have descriptive statistics that allow summarizing data using very simple computations, such as the mean, the standard deviation, or box plots. So these tools can be used on univariate data or bivariate data, or sometimes on data with 3 variables. exploratory statistics allow investigating or exploring big data sets in terms of number of columns. So we have dimension reduction techniques such as PCA or MCA, and we have also segmentation techniques such as AHC or K-means. And both descriptive and exploratory data analysis tools allow us to extract hypotheses or to fish for information without necessarily having a very precise question to answer. Whereas statistical tests allow to accept or reject a very precise hypothesis, assuming error risks. So statistical tests, most commonly used statistical tests are the t-test, ANOVA, correlation tests, or chi-square. So the descriptive and exploratory approach is very complementary to the statistical tests approach. And then at the end, we have modeling methods, which help us understand the way a variable evolves according to a set of other variables. So modeling tools include regression, ANOVA, ANCOVA, logistic regression, Poisson regression, and on and on. Today we're going to talk about ANOVA, which actually spans more or less statistical modeling and statistical testing and a bit of descriptive statistics, as it includes computations of means. And it includes a specific test, which is based on a variance ratio, we'll see. But it's part of statistical modeling, because you'll see that the ANOVA is a model that includes the model itself and residual error. Let's do a small reminder on statistical testing, which is very important for understanding ANOVA. So statistical tests allow to accept or reject a very precise hypothesis, assuming error risks. Let us ask a question. Are averages A and B the same? Statistical tests allow answering questions whose answer is yes or no, usually. Statistical tests involve two hypotheses that challenge one another. The null hypothesis, which can be written as follows: H0 average A equals average B. So null hypotheses generally imply an idea of equality. Whereas the challenging hypothesis, which is the alternative hypothesis, generally implies an idea of a difference. It can be written as follows in our example. So average A is different from average B. Statistical tests compute what we call a p-value. And this p-value will let us decide on the rejection or not of the null hypothesis and the acceptation or not of the alternative hypothesis. The p-value ranges between 0 and 1. So usually, if the p-value falls below a certain threshold, alpha, we reject H0 and we accept HA, assuming a risk proportional to p-value of being wrong. So usually if p-value is lower than this risk threshold, we can reject the hypothesis that the averages are equal. So this is very important to know for the remaining of the webinar. Now we talk about ANOVA. ANOVA is a modeling method with a quantitative dependent variable and qualitative independent variables. What do I mean by a modeling tool? So suppose you are investigating the salary of people from different origins, and you have a sample of people from Earth, a sample from Pluto, and a sample from Mars. The black circles, the black bubbles, are the means or the averages, average salary. Then the blue dots are the real data points. Here you have a dependent variable that is salary. Usually the dependent variable is placed on the y-axis. You have an explanatory variable or an independent variable, which is origin, and here it's qualitative. So we can apply an ANOVA model. The ANOVA model can be represented as such on the chart. How can I describe this? A model implies an equation that links the dependent variable to the independent variables with parameters. We can write it down like this. So salary equals the average of some reference level plus the distance to this reference level of the average of the considered level. So suppose you take some arbitrary reference level, which is Earth. We could have taken also Pluto or Mars. So if we take Earth, this would be the average of the reference level, this bubble here. And then distances of the other averages to this reference level are represented with those arrows. So if I want to take the average of the salary of people from Pluto, according to our ANOVA model, I would take the average of Earth plus this distance, this arrow. So basically we have three parameters. One parameter for the average of the reference level and two parameters for the distance between this average and the two possible other averages. This is my model. And each statistical model usually includes what we call residuals. The residuals are the quantities the model was unable to capture. So the model was unable to run into each and every single data point. There are some distances the model was unable to capture, and those distances are represented with those red arrows we call residuals. So the residuals are the part of variability the model was unable to capture. It's very important to keep residuals in mind for the meaning of ANOVA. Here's the main data set we'll be playing around with during this webinar. So we are evaluating spiciness in three different sauces. Sauce 1, sauce 2, and sauce 3. So here on each row we have one taster or one consumer who tasted the sauce and who graded the spiciness on a score, for example, ranging from 1 to 10 or from 0 to 10. Those are my observations. And I ask a question. Does spiciness change according to sauce? Starting from this, I'd like to run some statistical model. So let me first identify my dependent variable and my independent variable. Spiciness is the variable I want to try to explain or to model. And here spiciness is quantitative. And the sauce will be the independent variable because I want to try to explain spiciness according to sauce. So this is my independent variable, which is qualitative. So here an ANOVA model could be appropriate. So as you have seen, I've asked a question whose answer is yes or no. So there's some kind of a statistical test that will be involved. How does this test work? Let me show you first the means chart of spiciness according to the sauce and talk about statistical jargon around ANOVA. So here I have my dependent variable, spiciness, and my independent variable, sauce, which can also be called a factor in ANOVA. The orange bars are the means, and the error bars are the variability of each sample. S1, S2, and S3 are factor levels. We are talking about statistical tests. So a statistical test involves a null hypothesis and an alternative hypothesis. Here are my hypotheses. So according to the null hypothesis, the mean of S1 equals the mean of S2 and equals the mean of S3. The alternative hypothesis is at least one mean is different from the other means. So we are going to compute some p-value, and if this p-value falls below a certain risk threshold, we'll be able to reject this hypothesis of equality of the means and accept the hypothesis that there's at least one mean spiciness that is different from the others, taking a risk of being wrong, of course. Here we have one factor, so we only have one explanatory variable or one independent variable. So we're going to run what we call a one-way ANOVA. Now, how does the p-value of the ANOVA, how do we compute it? Or why do we say ANOVA, or Analysis of Variance? Let me take this chart once again. The statistical effect of the explanatory variable or of the independent variable is based on a variation ratio. Let me take one first source of variation in this chart. There it is. The variation between the means, the three means of the levels of SOS, is called the between group variation. And this is what characterizes our ANOVA model. So the largest this arrow, the more significant the SOS effect. So the larger this arrow, the more likely we are to reject the null hypothesis. But this is not enough actually. We should take into account the residual variation, which is right here. The within group variation, which is called also the residual error. Actually, ANOVA is all about the comparison between the within group variation and the between group variation. So if you have a very large between group variation, but if your within group variation is also large, then your effect won't necessarily be that significant. But if the green arrow is very large compared to the red arrows, then your model will likely be significant. The computation is quite simple. You simply compare the variances like this using a ratio we call F. So between group variation divided by the within group variation. And the higher this ratio, the lower the ANOVA p-value, and the more likely we are to reject the null hypothesis of equality of the means. So this is how the p-value will technically be computed. Now it's time to run our first demonstration on XLSTAT. So there's my data set. I have my data set in Excel. I have one column for SOS and one column for spiciness. And this is XLSTAT. It appears in the form of an additional tab in Excel. We have all of our statistical features stored in those menus. So there are many statistical features for visualizing data, analyzing data. And at the end, the ANOVA can be found under the modeling data menu. Here we go. So as soon as I click on ANOVA, the dialog box appears. So under dependent variables, I will select the dependent variable I want to work on, which is spiciness. So I select it like this. The explanatory variables are all qualitative. Actually, there only is one. So I select it like this. I click OK when I'm ready. And I'm going to focus on this table, which is the analysis of variance table. So first of all, there are two important numbers I want to stress on, which are those. This is the between group variation and this is the within group variation, and this is the ratio between the two sources of variations I told you about. So the larger this ratio, the lower the p-value. So here the decision can be taken. The p-value is lower than a risk threshold, say 0.05. We can reject the null hypothesis and accept HA while taking a risk of 4.9% of being wrong. So this risk is the p-value. Is this result really valid? Remember, there are conditions of validity in statistical modeling. So validity on assumptions on the residuals. There are basically four main assumptions. First, the independence, so no autocorrelation and one measurement per individual. The normality of residuals, so residuals should follow a normal distribution. Not too many outliers, in general no more than 5% of outliers among residuals, and equality of residual variances. So I propose to take each of these assumptions and verify them individually. First of all, the independence assumption. I will suppose that the independence is assumed. based on the way I constructed my experimental design or my data. So each row corresponds to one taster. There's no reason to think that there's a link between one row and the other. So there's no obvious relationship between measurements. Then, checking for normality. What I propose here is launching a normality test on residuals. So let me get back to my ANOVA report. If you scroll down in the report, you will see a big table with one row per observation and many columns. And these columns include what we call the residuals. So you have a column for residual and column for standardized residuals, and we are going to launch tests for normality on one of these columns. Actually, the normality tests will give exactly the same result whether you launch it here or here. So normality tests in XLSTAT are located under describing data. There we go, normality tests. Here I will select residual, my residual column, and I select here the normality test I want to launch. So there are 4 of them. I will just select the Shapiro and Wilk test, which is one of the most commonly used tests. There we have the result. We have a statistical test, so the result is linked to a p-value. A p-value with a null hypothesis and a challenging alternative hypothesis. Let's have a look at this null hypothesis. The variable from which the sample was extracted follows a normal distribution, whereas an alternative hypothesis is the variable from which the sample was extracted does not follow a normal distribution. With a p-value as big as this one, we do not reject the hypothesis that says that the sample was extracted follows a normal distribution. So we can say that the normality assumption is respected. Now there's another way to check for this assumption. You can look at the QQ plot right under. So here in the QQ plot, the dashed line represents a normal distribution, and the blue dots are your data. So if the dots are narrowly distributed around this line, then you can assume that they are normal. They follow a normal distribution. And usually this method might be better than the statistical test when you have few data points. Then checking for the equality of variances. Here again, I propose to launch a statistical test. So the equality of variances can be launched directly on the data. You're not obliged to launch the test on the residuals. The assumption says that variance is linked to all of the levels here should be equal. So variance linked to source 1 and linked to source 2 and linked to source 3 should be equal. Variance tests are located under parametric tests. There we are, case sample comparison of variances. I click on it. So under data, I select my dependent variable, spiciness. Sample identifiers are here, the source. I click OK when I'm ready. We have a statistical test, so here again, we also have a p-value linked to a null hypothesis and its alternative equivalent. The null hypothesis says that the variances are identical. The alternative hypothesis says that at least one of the variances is different from another. But the p-value does not allow us to reject the null hypothesis that says that the variances are identical. So here, once again, we can conclude that the assumption is respected. We still have one remaining assumption. We've seen the independence assumption, the normality assumption, the variance equality assumption. There still is the checking for outliers assumption. Here what I recommend is looking at this chart, which is provided by XLSTAT, the standardized residuals for spiciness. Here each line corresponds to one observation, and the values represent the residuals. So the residuals linked to each observation, actually the standardized residuals. So as a rule of thumb, we can consider as outliers the residuals that are lower than -2 or higher than +2. Here we can consider that we only have 2 outliers exceeding the limits, which is more or less 95%, only 5% of our data. So we can also conclude that our residual outliers assumption is respected. So our ANOVA is thus reliable, now that we've seen all of these assumptions. But there's something a bit frustrating about our result. Here are our null and alternative hypotheses. So the null hypothesis we've rejected and the alternative hypothesis we accepted. We have chosen HA. Can you have a more precise insight on which specific means are different from one another? HA states that at least one mean is different from the other means, but it doesn't necessarily say which mean is different actually. But we could be very interested by knowing which pairs of means are different from one another. So to answer this, we can use techniques that are called multiple pairwise comparisons. So multiple pairwise comparisons will compare all of the different means to one another. So we'll compare S1 to S2, S1 to S3, and S2 to S3. So to launch multiple pairwise comparisons, just go back to XLSTAT and to the ANOVA feature under modeling data. Here it's still configured as I configured it before. You can go to outputs, means, so outputs, means, and activate this option, multiple comparisons. Here you can activate pairwise comparisons, and there are many available methods to launch pairwise comparisons. There's Stuckey, Fisher, and many other methods. Here I will use Stuckey HSSD, which is one of the most commonly used methods for pairwise comparisons. I click OK. So the results relative to multiple comparisons in XLSTAT appear at the bottom of the result report usually. And there are many ways of representing these results. There's this way, this way, this way. I will focus on this way. Here I have a chart with spiciness on the y-axis and the different means that are captured by the ANOVA model. So a mean linked to SOS S3, S1, and S2. XLSTAT has automatically sorted the categories according to the mean. So the highest mean is in the beginning and the lowest mean is at the end. As you can see, there are letters which are associated to each mean, A and B. Those letters are the key to the interpretation of multiple pairwise comparisons. Two means having at least one letter in common are not significantly different. If we take S3 and S1, we have the A in common. So those two means are not significantly different. In opposition, two means without any letter in common are significantly different. Here, if I take S3 and S2, A and B, we don't have any letter in common. So we can say that S3 and S2 are significantly different. So now we can conclude precisely which sauces are significantly different from one another. We see that S3 is the spiciest sauce, and S2 is the least spicy, and we have an intermediate sauce which is S1. Now we have investigated ANOVA from the beginning to the end. So we saw how to launch a general model, we saw how to check for the ANOVA assumptions, and we also launched multiple pairwise comparisons to investigate our result further. So before switching to the two-way ANOVA, I wanted to tell you a bit about a non-parametric equivalent of the one-way ANOVA, which is the Kruskal-Wallis test. But before talking about this, I will take our first set of questions. Can you talk about the difference between a one-way ANOVA and two-way ANOVA? Yes, of course, this will be the last part of our webinar. Suppose I have given 7 treatments and recorded them for 2 days, and I want to test if the 7 treatments differ on response variable or on the dependent variable. Which test should I use? Is it one-way or two-way? So here basically you have 2 factors, which is time and treatment. Treatment has 7 levels and time has 2 levels. But as you are following your dependent variable over time on the same individuals, you are violating the independence assumption that could be dealt with using repeated measures ANOVA or mixed models. For this, you have an appendix at the end of the presentation that talks about mixed modeling, and you can also check the mixed models tutorial on the XLSTAT website or the repeated measures ANOVA model. What to do when one or more assumptions are not met? So it really depends on which assumption is not met. But usually for the normality assumption, which is often not met, or the variance equality assumption, you can perform a transformation of your data. For example, you can transform your dependent variable using a logarithm. You use the logarithm or the square root transformation. And you relaunch your model and try to see if you get closer to the normality assumptions. And if that is the case, it's very good for you. But if that is not the case, then you can also use a non-parametric equivalent, which is the Kruskal-Wallis test I'm going to talk about right away. So the Kruskal-Wallis test is non-parametric equivalent for the one-way ANOVA. I will launch it here on the same data and interpret the result. So the Kruskal-Wallis test is located under non-parametric tests. Comparison of k samples. Here I have the Kruskal-Wallis test dialog box that appears. Under data, I take spiciness, and sample identifiers, I take the sauce. Here, as you can see, you have also multiple pairwise comparison procedures that are specific to non-parametric testing or to the Kruskal-Wallis test especially. Click OK. So this is a test once again, so I have a p-value. My p-value is very high compared to the risk threshold alpha. It doesn't really allow me to reject the null hypothesis. But this null hypothesis, we rejected it when we used ANOVA. So why do we have a difference? If you remember the statistical testing webinar, I talked about the difference between parametric tests and non-parametric equivalents. I said that usually parametric tests have more statistical power than non-parametric equivalents, which means a parametric test is more likely to reject a null hypothesis if this null hypothesis is wrong compared to a non-parametric equivalent. So this really illustrates well what I said, which means that parametric test rejected the null hypothesis, which is ANOVA, and its non-parametric equivalent could not reject it. It didn't have as much statistical power. This is why we often recommend to use parametric tests when the conditions are respected. So at last, two-way ANOVA. Somebody asked a question about the difference between one-way and two-way. So we'll add another independent variable, and we'll talk about something very interesting, which is the interaction between the two independent variables. So if you add another independent variable, you are not talking anymore about a one-way ANOVA, but about a two-way ANOVA. So here's how the real data set actually looks like. We have a third column in our data set, which is the judge column. We have 8 judges. Judges are tasters. Each sauce is tasted 3 times by each judge. So I lied a bit at the beginning of the webinar. I said that all the observations are independent, that each row corresponds to one taster, but this was wrong. The independence assumption was not actually respected. I'm sorry about that. So we have this additional column, the judge column, and we're interested also in the effect of judge on the evaluation of spiciness. So here we still have one dependent variable, which is spiciness, but we have 2 independent variables or factors, which is judge and sauce. The questions we are asking now are the following. Does mean spiciness change according to sauce? Does mean spiciness change according to judge? Does it change according to the interaction between judge and sauce? What do I mean by the interaction between my 2 factors? The interaction effect can be translated as follows. The effect of one factor depends on the level of the second factor. For example, the sauce effect depends on the judge. So let me tell you a bit more about this interaction effect. I'm going to take a very simple case. Imagine you have a very simplified case with only 2 sauces and 2 judges. So here's a list of possible outcomes. Among the many outcomes you can have in terms of results, here is a series of 4 possible outcomes. We have 4 charts, and the y-axis of all of these charts is spiciness. Okay? Within each chart you have 2 pairs of bars. One pair for judge 1, another pair for judge 2. Within each pair you have 2 bars, a green bar and an orange bar. So the green bar is sauce 1, the orange bar is sauce 2. So this is a very convenient way to illustrate a two-way ANOVA in a chart. We have our 2 factors represented here, the judge factor and the sauce factor. I will investigate each case separately. First of all, let's have a closer look at this chart. What kind of effects do we have? Do we have a judge effect? Not really. If you take the average of the 2 bars for judge 1 and the average of the 2 bars for judge 2, the 2 averages will be identical. So we don't have a judge effect. But as you can see, the sauce effect is significant, which means the orange bar are higher than the green bars. Here in opposition, if you take the average of judge 1 and the average of judge 2, we see clearly that there is a judge effect, whereas the sauce effect is not significant. If you take the average of the green bars and the average of the orange bars, you have identical averages. Here you only have judge effect. And this is where the two-way ANOVA with the interaction becomes interesting. Check this out. Do you have a judge effect If you take the average between those two bars and those two bars, the average between those two bars, you get identical averages, so we don't really have a judge effect. You have a sauce effect. So the average between greens and oranges is the same. But if you take the sauce effect within each judge, you see that there's a very huge difference. Judge 1 thinks that sauce 2 is way spicier than sauce 1, whereas judge 2 thinks that sauce 2 is less spicy than sauce 1. This is what we call an interaction effect. So the sauce effect depends on the level of judge. Here we see that we have a strong judge effect. The average for judge 1 is low, whereas the average for judge 2 is high. Also, the pattern of sauce effect is very, very different according to the judge. So we can also say that we have a judge-sauce interaction effect, which is strong. Now, can we have a sauce effect in this case? Well, if we take the average of greens and the average of oranges, we could have some more or less strong sauce effect. But I didn't write it down here, but we could have added it. Now, how do you run a two-way ANOVA in XLSTAT? Take modeling data and ANOVA. Here my dependent variable is still spiciness. My independent variables are two now. We have sauce and we also have judge. The column was hidden here. I tricked you. In the Options tab, it's very important to activate the Interactions option. And here we have a two-way. We want to look for a two-way interaction. You cannot look for a three-way interaction as we only have two independent variables or two factors. In the outputs, I will activate this option, which is very important. This option will let me evaluate the effects of judge alone, of sauce alone, and of the interaction between sauce and judge. I can also ask for multiple comparisons, of course. Here I will just deactivate them. Once I click on OK, XLSTAT asks me which effects do I want to include in my statistical model. I want to include everything, judge, sauce, and judge multiplied by sauce. I click OK. Here we are. I will focus on these tables. So type 1, sum of square, type 2, and type 3. And I strongly recommend that you usually check the type 3 sum of square statistics. The type 3 is a very robust, which is the least sensitive to unbalanced designs. So if you have an unbalanced designs, which means you don't have the same number of repetitions in all the combinations of the levels from your independent variables, you have unbalanced designs. So this typically occurs when you have missing data. So suppose you have judge 1 who omitted to taste the last sample, the third sample of S2. Here you only have 2 repetitions, whereas for sauce 1 you'll have 3 repetitions. This is a typical case of unbalanced designs. And if you have unbalanced designs, I really recommend that you take type 3 sum of squares tables for the interpretation. But if you have very strong unbalanced designs, maybe ANOVA is not appropriate anymore. So I will comment on this table right here. So first of all, as I told you, just prefer the type 3 sum of squares table, especially if the design is unbalanced. Then each row represents one source of effects. You have the main effects here, so judge and sauce, and the interaction effect, which is judge multiplied by sauce. As you can see, each effect is linked to an F ratio and to a p-value. And here I have written all the H0 hypotheses. So for the first effect, you have mean J1, mean judge 1 equals mean judge 2 equals mean judge 3. For the second one, you have mean sauce 1 equals mean sauce 2 equals mean sauce 3. And for the third one, you have The mean change from one source to another depends on judges. You can also write it the other way around, so the mean change from one judge to another depends on the source. So the decision, the three p-values are lower than alpha, so we reject all three null hypotheses while taking very low risks of being wrong. Now, it's very nice to have an interaction effect here, but how can we interpret it? Well, there are many ways of interpreting an interaction. You can either launch multiple pairwise comparisons to see which combinations of levels of the independent variables are different from one another, or you can also check what we call an interaction plot. At the end of our two-way ANOVA result report, we have this chart, which is very interesting. On the y-axis, you have spiciness, and on the x-axis, you have one of the two factors involved in the interaction. Here I have included the source, so S1, S2, and S3. Then each judge, or each level of the second factor, is represented with a line of different colors. If we didn't have a significant interaction effect, we would have had the same pattern, the same kinds of lines for all the judges. So we could have had just the same V line, a line with the shape of a V for everyone, like this. But here we have very different patterns. For the purple judge, we have a decrease from S1 to S2, then an increase from S2 to S3. Whereas for the gray judge here, so judge 8, we have an increase from S1 to S2, then from S2 to S3. So the patterns of source effect differ according to the judges. This is how we interpret the interaction. So to sum it all up, ANOVA is a modeling tool with a quantitative dependent variable and qualitative independent variables, which are called factors. ANOVA involves a test based on the between group divided by the within group variation ratio. We have conditions of validity, of course, independence, normality, not too many outliers, and equality of variances. Multiple pairwise comparisons help identifying which specific levels are significantly different. The Kruskal-Wallis test is a non-parametric equivalent for the one-way ANOVA in case you are unable to get close to the conditions of validity. And multi-way ANOVA, like the two-way ANOVA, helps investigating main and interactions effects. Well, thank you very much for attending at least this webinar. Many of you have attended the 5 of them. You can download the 30-day trial by clicking here and discover our products here. I'm going to take the last questions. In your data, the judges evaluated each source in triplicate. Can I still use one-way ANOVA if judges evaluated the sources just once? What is the impact? Well, if you only have one repetition per source and per judge, you won't be able to compute an interaction effect. You need repetitions per combination of judge and product to be able to have an interaction effect. So here in your case, you will only be able to compute main effects, so main judge effect and main source effect. Can you use a Kruskal-Wallis test for a two-way non-parametric ANOVA? Well, unfortunately, no. The Kruskal-Wallis test is designed only for one-way ANOVA. Well, thank you for the questions. If you have any other question or demand, don't hesitate to send them to me by email. And I hope to talk to you once again in another season of webinars. Have a nice day. Bye-bye.